together on the group. Yeah, the recording has started. We'll start with where we had stopped yesterday. The next slide that we need to speak about in oceanography is something I don't know how many of the students have seen this curve before. I'm doubting if the state board students have seen this, basically because I for sure know that this is not taught at the SSC level. I feel that this must have been done at the NCERT level. So this is called as the hypsometric curve. Okay, there are various interpretations of the hypsometric curve as such, but then what exactly does this show? This shows the distribution of land and water on the planet. Why do we do with oceanography? Obviously, oceans occupy as much as 75% of the surface. So normally, on land surfaces, we while dealing with land surfaces, we don't actually do hypsometric curves, but then we do this with reference to it can be done with reference to any land surface or water surfaces as such. It's basically, you'll see that the relief between the highest point of the earth and the lowest point of the earth as such, and you see that on the x-axis here, it's so many million kilometers as such. The total area of the earth is 520 million square kilometers as such. Now, just to give you a comparison, if the earth is 520 million square kilometers, India, by the way, is 3.2 million square kilometers. China is 9.6 million square kilometers. And most of the countries are around that, except for Russia, I would say it's a bit larger, but then Brazil, US, Australia, all of them are less than 10 million square kilometers. As such, India is 3.2 million square kilometers as such. Okay, you see that from the highest point, that's obviously Mount Everest, 8848, to the total land area is around 139 million square kilometers, and of course the area of the oceans is around 360 million square kilometers as such. So I believe what they have done is they have rounded up to 500 million square kilometers as such. Now, a few things that with regards our exam is concerned, and with reference to a few competitive aspects are concerned, you can see that the average elevation of exposed land is 841. Now, actually, I would say this line, by the way, is the average elevation. In the real sense of geography, I would say the average elevation is 841, and the average elevation of the, say, the average depth of the oceans, that's this line, 2070 meters below mean sea level. It does not have much of a reference as such. It actually is more of a statistical, or I would say mathematical observation rather than anything else, because anything on an average does not make much of an impact in geography, particularly as such. You have to be there and understand what all of it is there. 29% of land surfaces, and the rest of the 71% is oceans as such. You'll see that the Mariana Trench is nearly 11 kilometers deep, so the Mariana Trench could be somewhere here all the way down. Okay, I feel we've done most of the things as such, and there's one more thing which again, this is the hypsometric curve as such. A few more points that we can note from here. And this, of course, speaks in terms of meters and feet. Okay, and once again, the average elevation exposed and the average depth exposed as such. I think there is a difference between these two diagrams. average elevation 841, average elevation 875, average depth is 2000 meters, and here it says it's 3800 meters. So you'll see that different surfaces are going to be, different publications are going to show you different levels as such. This could also differ on what is the mean sea level. Okay, different scientists will take different mean sea levels, so that could impact it also. So that is something that we have to take into mind as such. So that's all about the hypsometric curve. And when we speak about the overall distribution, you'll see that oceanic ridges, volcanic islands, ocean basins, this is how the distribution takes place. Continental shelf and slope. We are going to do the configuration of the submarine relief, but shelf and slope occupy only 11% of it. Ocean basins occupy a very large percent, and so do oceanic ridges. Okay, if we total up ocean basins and ocean ridges as such, they come to around what? 52%. So half of it is that. So we have to keep that in mind. Scales, I've already said, do keep a lot of importance as far as geography is concerned, rather than sheer numbers as such. Okay, so that's something that we have to understand. Then continental rise, which is another aspect of volcanic of submarine relief, occupies for to around 4% as such. Now, actually, you'll see that continental shelf and slope should also be classified under oceanic surfaces. So I'll just make it what it looks like. Otherwise, in the bar diagram, as such, seems to be a mistake by the person who has put up this particular diagram. So it actually should be looking like this. Okay, so this is another aspect. As I said, I would be hurrying up a bit because I plan to finish off the portion today. Let us see. The two hemispheres, as they are normally called, this obviously is the southern hemisphere, and this obviously is the northern hemisphere. We are looking at these hemispheres from the poles. So we'll see that Greenland is here, India is here. Okay, so we'll see that India, as a matter of fact, is larger than Greenland. But on a world map, normal world map, you'll see that Greenland seems to be as large as Africa, but it is obviously not. Okay, this is North America. So you'll see that you have a lot of land surfaces in the northern hemisphere, making it up to be called the land hemisphere. And as far as the southern hemisphere is concerned, you'll see that only the southern tip of Africa and Australia and the southern part of South American continent with the Antarctic continent in the center make a lot of water available to us. And that's why this is called as the water. And that's why you'll see that when we spoke about the currents moving yesterday, and in fact, you must have, we have spoken about the Southern Ocean as such, okay, because this cold continent impacts the water around it, and the water in fact flows in its own system. That's why we have evolved a new ocean called as the Southern Ocean as such. Okay, so that's about the land and the water hemisphere. Now, putting it all statistically, putting it up mathematically, how does it look? See, obviously, you'll see that this is the northern hemisphere and this is the southern hemisphere. You'll see a large amount of land. See, comparatively, you're going to have a significant amount of water, but you'll see that particularly when you compare it with the southern hemisphere, you have large land areas in the northern hemisphere as such. However, you'll see that what is called as the antipodal arrangement as such. Normally, it has been seen on the Earth that exactly opposite to a particular surface, you have the other surface. In the sense, opposite to land, you have normally you have water, and opposite to water, you normally have land. Of course, it's not a perfect match because land is only 30% and water accounts to around the remaining 70%. But that's called as the antipodal arrangement. Okay. In most of the cases, you'll see that it is in that particular way. Uh, an obvious question would be, what difference does it make? Okay. You'll see that the difference being that particularly land. Okay, you don't have land areas against land areas. That's an interesting observation that we have to keep in mind. Uh, Northern hemisphere, again, you'll see that between 15 degrees and I would say 70 degrees, you have a lot of land as such. But as you come near the equator, yes, you have land, but water increases. And we spoke about it yesterday also that in Asia, you don't have much land along the Indian Ocean, particularly. You don't have much land along 0 degrees except for the Indonesian islands and other islands as such. As you move towards the southern hemisphere, you'll see that the maximum amount of land that you have is around 30 degrees of latitude. As you go further down, it goes tapering with an exception that all the way down you have the Antarctic continent, which occupies the South Pole. So you don't have much water near the South Pole. Okay, so these are a few other observations that we have to keep in mind when we speak about distribution of land and water, the northern hemisphere, the land hemisphere, and the southern hemisphere, the water hemisphere. Now, uh, this is basically how the ocean surface looks like. Okay, and these are the different names. You don't have to remember these names. You will not have questions on this, though it is a part of your syllabus. We have not had ample amount of time to study the submarine relief of the respective oceans. So you will not have questions on that. Don't worry about that as well. But then this is what the submarine relief looks like. And with this, I would also like to refer to what is called as the theory of sea floor spreading. Okay, you'll see that somewhere in between Wegener and plate tectonics is this theory of sea floor spreading. Around this theory, you have this theory of convectional current. Sea floor spreading, I think it was Harry Hess who gave this particular theory as such. Now, there's a very interesting logic behind this, and it's very important to note. And the whole theory of seafloor spreading, I'll just put it in a nutshell as such. Normally, what used to happen is because human beings, and in say 100 years ago, 100 years ago by now would have been the time wherein uh, Wegener was all around the place. People were fighting in the sense, intellectually fighting against his theory and so on and so forth. He had put forth his theory in 1912, and it would have been 2021, the end of the World War. 1921, the end of the World War. And India was to find that its population was less, literally less than the census of 1911, and so on and so forth. A lot many things were happening at that particular point of time. And because volcanoes, obviously you don't see volcanoes which are happening beneath the oceanic surface. So you saw these volcanoes on land only. So the general belief was that land is fresh. Land is something that renews itself regularly. However, oceanic surfaces are old, and they must have been millions of years old, if not billions of years old. However, you'll see that what is called as the Paleomagnetism Theory, uh, and of course when these I don't exactly remember the dates, the year as such, but then they took up this activity around the Second World War to lay down a cable of communication between Europe and uh, America. That's Europe here and America. Okay, this is where they were supposed to be laying a cable. And while they were surveying, they found this mid-Atlantic ridge. This was a fantastic discovery, basically because of the fact that when they saw went into the details of understanding this, they found that the seafloor along this particular Atlantic ridge as such, you had a lot of volcanic activity, and it was this volcanic activity which was pushing these two continents away from each other. Of course, this was taking a cue from the Wegener's theory. This was proved beyond doubt by the fact that the rocks which were nearer to the center of the mid-Atlantic ridge were younger, and the rocks which were away from the Atlantic ridge were older. And this eventually was traced. It was believed that you would have Atlantic ridge, a ridge, volcanic ridge, the center of all the oceans as such. However, except for the Atlantic Ocean, it does not run through the center of the other oceans, the Indian and the Pacific as such. But then we did have the extension of this ridge into other oceans also, which brings us to it connecting how the plate tectonic theory later on must have developed as such. But coming back to the seafloor spreading, theory of seafloor spreading, what was astonishingly known to us through that is that as compared to land, in fact, it is the oceanic floor which is renewed more regularly, and none of the oceanic floor is more than 180 million years old. Okay, 180 million years old as compared to, you could say, the 4.6 billion years that the Earth has been living for, is something which is very, very astonishing. Okay, so the ocean surface is continuously on the move, while land surfaces are very, very old as such. And you'll see that we speak about these shields as such. You have the Canadian shield, you have the Brazilian shield, you have the Siberian shield, the African shield, and of course you have the peninsular part of India, which for sure are a billion years old at least, if not less. Why does this happen? Basically because you'll see that the land is made up of less dense material, while ocean basins, under the pressure of the water, you have volcanic eruptions get transformed into basalt rocks. Basalt rocks are more dense, and that's why they stay below. And as they move, you'll see that they ride beneath the granitic rocks, and that's how you'll see that it's all the you'll see that if you remember what we spoke about the plate tectonic theory as such, it is believed that the plate tectonic theory starts with the fact that the whole of these surfaces are like the material moving on a conveyor belt, and this comes out of all this understanding that the oceanic surfaces particularly are renewed regularly. The oldest of them is not more than 180 million years old. Much of this oceanic surface is much less. The oldest is 180, but normally it tends to be between 100 and 150 million years old only. A few million years here and there only, but otherwise that's what. And you'll see that these ridges are associated with plate margins also. Okay, if you remember the plate tectonic theory, you can identify a few plates at least along these margins as such. Okay, they are known by different names in different parts of the oceans. However, remember that the oceanic ridge is a continuous way of nature actually renewing the oceanic surface as such. How does this happen? You see that while you have a ridge at one particular end, at one particular location, you are going to have trenches on the other. Okay, and we are going to see that as well. Okay, this is how actually the distribution of a cross section you'll see across. Okay, you'll see this is the Rift Valley, Mid-Atlantic Oceanic Ridge as such, and you move away from it. Okay, as I said, you are going to have old rocks, you are going to have older rocks, and so on and so forth in this particular direction. Okay, so this is fresh and this is old. Okay, then uh, while we are doing this, a few other things that also we should be doing is that if this is land, you're going to have a very shallow surface which is called as the continental shell. Okay, and then you're going to have an abrupt fall that's called as the shelf break as such, and then you're going to have what is called as the continental slope. Okay, and then you're going to have a gradual increase which is called as the continental rise, and then you are going to have the ocean basins, etc., which is called as the abyssal plane. I purposely put up multiple diagrams of this so that we can revise it again and again as such. Okay, this is the more common one as such. Here you can see the actual slope as such. The shelf is very shallow and it's not very steep as such. Then you have shelf break, and then you have the continental slope, below which you're going to have the continental rise. A lot of the material that goes into it, it accumulates in this particular area. And very deep, let's say 4 kilometers and beyond, you're going to have what is called as the deep oceanic floor. Okay, now though this is seen here, you'll see that this is very exaggerated. Actually, you'll see that it would look something like this. Okay, you can hardly see the changes happening, but that is how actually that is the scale at which all of this is actually happening as such. Okay, when you are matching the x versus the y angle as such. Okay, because here in the upper diagram you will see that while you say this is 100 kilometers, you are going to say this is 5 kilometers, matching it to that. So this is a very exaggerated diagram. It actually should be looking something like this. It looks like something like this, very gradual. This is the information about various oceans. We're not going to do this. This is another photograph of I would rather say, imaginary picture about how the coastal plain goes into the continental shelf and slope, continental break, and then the abyssal plains. You have canyons and so on and so forth, seamounts in some areas. This is how it looks like in some areas. Now, this is a bit of a complex diagram, but then you see that this is how continental shelf, continental slope, deep oceans. It's again further divided as such, and you'll see that this is available at this particular link on Google, the mid-oceanic ridges and others. Okay, this is how geologists have studied the whole ocean surfaces, and this is how they divide it into various parts and subparts as such. You will see that around India, you will see that the oceans are very shallow, but you'll see that the Pacific comparatively is very deep. It's something that we can say. We do say that along equator in the Asian continent, we don't have much land as such, but you'll see that it's not very deep also. Water is occupying the area as such. Here you'll see that this is an extension into Australia. These are a few observations. I'll purposely not go into the details of that. Okay, now this is what actually keeps on happening. Okay, I'll not go into explaining all these. Okay, I'll do one thing. I'll just run through the explanation of this. Okay, you'll see you have the continental shelf here, and then you have the continental slope here. Here you have some seamounts here, and then you have the mid-oceanic ridge here, and then you have these trenches here. What actually happens is this is something that works like a conveyor belt. Okay, that the land is going to form along the ridges, and you'll see that as it moves, it's going to push this part, and this is going to go in. Yes. Okay, so this is what is called as the conveyor belt system. As such, you have these trenches margining many continents of the world. One most popular one is along the margins of South America. That's here you have the trench as such. Okay, and the Pacific plate is supposed to be opening into the trench. One more trench is along this particular path. Okay, so that's about it here. And yeah, this is the more I would say elaborate diagram showing us the various components of the submarine relief. Okay, in addition to the ones we have already seen, we have seen continental shelf, we have seen continental slope, you have submarine canyons here, continental rise here, the abyssal plain, abyssal hills are also there, and then you have, okay, yeah, we also spoke about the conveyor belt in the earlier one. Okay, you'll see that the ridges are going to cause formation of land here, and the older land is going to be pushed, and as it tends to be pushed, it's going to go down here into the trench, and it's going to complete the convection cell, and you'll see that when it goes down, it's going to become all magma, and then it's going to come up, and then it's going to be flowing like lava. So that's another explanation to all these things. And yeah, another example. See that the mantle here, the oceanic crust, the continental crust, which tends to be thicker. That's what Wegener also said. But of course, Wegener had other ideas. This is the trench I am speaking about. Land is going to land, or rather, I would say the crust is going to sink in oceans, and then it's going to come up somewhere here. Another diagram showing you the composition of. Okay, so you can see that you're going to have the shelf, the slope, the rise, and the abyssal plane. SSRA is the sequence that you can keep in mind from land into water. Once again, depth of 200 meters, till the depth of 200 meters is continental shelf. To around 2000, the next distance, this is the slope. It keeps on sloping till around 2 to 3 kilometers as such, and then you have the rise at around 4 to 6 kilometers, below which you want to have the abyssal plane. Okay, this is 4,000. This is the 6,000. And then you're going to have oceanic trenches, which are very, very deep as such. Some oceanic islands keep on increasing. They have so much of wild magma that they pile on, and they could come up on the surface also. The Hawaii Islands are an example of this. Okay, for this to happen, okay, otherwise you'll see that they stay back as seamounts only, okay, which could be beneath the surface, but some of them rise all the way up only because if they are standing on what are called as hotspots, water hotspots. These basically are areas where you have hundreds of millions of tons of lava, which is there. I think we spoke about these hotspots in the first semester also when we were speaking about plate tectonics. These are a few basic things. Yes, I'm not going to speak about the temperature and the salinity, etc. But two things that we need to speak about is waves, okay, and tides as such. This is how basically you'll see that winds, yesterday in the clip we saw, the guy was saying that when the winds are going to flow on the surface of the waters, they obviously are going to pass on that energy onto the surface layers. The surface particles of water, they keep moving in a circular motion. But as they approach, that's in the deep water, but as they approach shallow waters, what happens is this circular paths, they get compressed because of the pressure applied by the land getting shallow, or the water getting shallow as you move towards the land as such. and that's why you're going to have spilling of the waves as such. It's also called as breaking of the waves. And you'll see that these spilling waves or breaker waves, you'll see here it's written breaker waves, are used for surfing. Okay, and you'll see that surfing is very popular in the southern hemisphere, particularly Australia and Brazil and Argentina and South Africa as such. And some of it is copied in California, etc. You see that surfing is not much practiced in the northern hemisphere. While you're thinking why this should be happening, the obvious reason being the winds are stronger in the southern hemisphere. So they pass on a lot of energy to the water, which is comparatively less as far as the northern hemisphere is concerned. So this is understanding geography the logical way, how you connect oceanography to climatology and oceanography to physiography, that's lithosphere as such. Okay, these are the dimensions of a wave as such, anatomy of a particular wave. You'll see that normally you have the crest and you will have the trough, and the distance between the two crests, subsequent crests or troughs, are going to be called as the wavelength. The height between the trough and the crest is going to be called as the wave height. Okay, now I'm not going to the details of this basically because we do this in physics as such. What is the frequency? What is the period? I don't think I have to go into the details of that for science students as such. Okay, this is actually what happens. This is a repetition of what we have seen earlier in deep waves. What happens is the wave movement and the energy of the wind makes these move in exactly circular one. But you'll see that as you go down, the pressure of the above one makes the motions very, very smaller and smaller and smaller. And what we're speaking about, these surfs and swashes and breakers as such, you see that what was absolutely circle here starts getting flattened as you start coming towards the land, and because of it, it loses its balance, and that's why it breaks. And that is why it's called as a breaker. So many terms used in English effectively in science are so very logical as such. Wave breakers, they call it, because the wave gets very, very imbalanced, and that's why it collapses. That's about it. And yeah, this is how it looks in deep waters. As you start approaching, the circular motion is pressed a bit, and that's why the wave breaks here as such. Okay, and it collapses down here. Okay, and that's called as the surf zone as such. Okay, you'll see that the foam, the white foam that you see is in the surfing area as such. These are basically energy generation units that you find in some places of the world. It's not being very economical, but you'll see that what they've done is they've just set it afloat, and this is literally like oars of a boat. Okay, with the rise and the fall of water or waves. Okay, this goes up and down, and while this goes up and down, this is connected here, and you'll see that energy generation takes place here. Yeah, coming to another aspect of movement of water is tide. Tide is a periodic movement. It's the first word that is important. Secondly, it is based on the gravity of the sun and the moon. Now you would say that there is no comparison between the gravitational forces of the sun and the moon. Yes, definitely. But because the moon is much nearer to the sun, to the earth as compared to the sun, you'll see that that formula, I think E is equal to mc square. Okay, you'll see that because it is nearer, though it is smaller in mass, you'll see that the force applied is competitive as far as the sun's force is concerned. Both of them are going to apply forces on the liquid surfaces as such, and the liquids get dominated because of that, and they move as such. So this is how you will see actually high tide, low tide, high tide, low tide. Now what you can do is keep noting here. Okay, this first the picture here, high, low, high, low. Okay, what you understand is this, you want to be alternating. Now just imagine as comparatively here, what is happening when the moon is actually I would say at an angle to the sun, then you're going to have a neap tide, as it is called. It's not only called as low tide, but the lowest low tide is a neap tide. But when the moon is along with the sun, in line with the sun, okay, sun, earth, and moon come in line to each other, then you're going to have the high tide, the highest high tide, which is called as the spring tide as such. Now this happens basically because when they are in line, okay, a new moon day or a full moon day, you'll see that the moon and the sun are going to impose their gravity together on the earth. But when the moon is at right angles as compared to the earth to the sun, then what happens is their gravity gets gravitational force gets divided, and the wave is not, tide is not able to rise that much, and that's why you're going to have a neap tide as such. Okay, you'll see the same position in the same area, spring tide and neap tide as such. That's another miracle of nature, I would say. Okay, tidal patterns, you have different types of tidal patterns. So you have what are called as, in low latitudes particularly, you have semi-diurnal. That's two high tides and two low tides per day. In high latitudes, you'll see that you have go to diurnal, one high and one low per day. And you could have mixed patterns in the mid latitudes. Okay, two highs and two low, but successive high tide levels that are very different from each other. That's mid latitudes for us. The type of the tide will depend on the position on the globe, where you are located on the globe as such, the depth of the water, and the contour shape of the ocean basins. You'll see that all these are going to affect the type of tide in a particular area as such. Okay, you'll see that these are, okay, you'll see that wherever it is in the interiors, okay, the water gets blocked, and that's why you have very high tides. Okay, so all these blue areas that you can see, okay, and India, you'll see that the Gulf of Khambat is where you're going to have very high tides as such. Okay, where the water narrows into a small inlet, you'll see that you're going to have high say higher potential areas for tidal resources. Okay, in these areas, it's not only that the tides get higher as such, but you can generate what's called as tidal energy in this. I have put up URLs for 3 clips on YouTube with regards these generation of electricity or energy from tides as such. You can note them down, or I will pass them on to you, or I'll do one thing. If I remember, I'll post this on the Excel sheet that I am making for the whole class for our reference as such. So this is as far as oceanography is concerned. I know I've been very fast, but then I've tried to give you a very fair idea of what happens in the oceans. A lot of the area of the oceans is still to be studied. Let me tell you, it's nearly double the area of the land as such. So, and of course, it's three-dimensional. You have to go deeper also. It gets difficult to study all these things. Here, we did not study a tsunami as such, okay, but a tsunami is very similar to that. This thing that we are seeing here, you'll see that if eruption is going to take place, this breaker is going to be much, much steeper, and is going to be much, much higher. And being higher, it will obviously come much further as far as land surfaces are concerned. That's the only difference between a normal wave and a tsunami. It's a very, very large wave, I would say. And the energy for this large wave comes from some earthquake movement in the ocean floors or some oceanic, floors. So this is not a tsunami. This is a breaking wave in in the southern hemisphere. This is certainly not one in the northern hemisphere. Northern hemispheric waves do not climb this high in distances as in heights as such. So I've tried to touch major points of oceanography, which would interest you all. And India has its own Institute of Oceanographic Studies as such. It's placed in Goa, the National Institute of Oceanography, as it is called. And you'll see that a lot of training for Indians who go on the Antarctic mission actually happens in and around this particular institute. And normally what happens is they travel from India to Africa, and from here they take a flight to Antarctica as such. Okay, if the contingent is small, they take a flight. If the contingent is large, then of course they take a ship, which needs to be an icebreaker. India presently has 3 stations on Antarctica. It would be fine if you could remember the names of all the 3. Okay, I'm giving you hints of questions that you could have. Okay, we will not do this. Not required here. Don't worry about questions, detailed questions on this. Just remember that you have this oceanic ridge, which other than Atlantic does not run central as such. So I feel I was so fast that I finished it off very fast. Anyway, but I think I have not missed out on any major things. So I'll stop sharing here. I'll end the show. Return back to our meet as such. What I've seen is many students in the second semester have not submitted their assignments as such. And when I compared their marks, they are getting around 7, 8, 9 out of 10. Now, let us be very frank. We know how we have scored these marks as such for majority of the students. I know all those gimmicks, and such students have opted out of it. Now, let me tell you that geography or any other subject, this is not a good habit to be practiced. I don't think so. Of the 135 students who took the exam, the 20 students, 20, 25 students that are attending the lecture right now may have done that. But and most of the names that I see are also the names who have submitted their own assignments as such. But let this be a lesson. Though you may not, okay, at any point of time in life, you are tempted of shortcuts. Let me assure you that there are no shortcuts in life, and we have to actually study things unless and until we are looking at a very bleak future. Yes. I'm going to stop here today, and with this we have finished off with our just